of the problem. The question is asking what indicator is best for detecting the equivalence point. This is an excellent question. The answer is not phenolphthalein. You guys are most familiar with that indicator phenolphthalein, which changes magenta in a basic solution. But in this case, guys, at the equivalence point, we've already seen that the pH at the equivalence point, I can't find it now, the pH at the equivalence point is going to be 5.27. That's going to be an acidic pH. And so you need an indicator which is going to change color once the pH reaches about that. Okay, so let's look at how to do that, guys. This is the last little bit of notes out of chapter 18. Okay, first of all, let's talk about what an indicator is here, really briefly for just a second. An indicator is usually a weak acid, okay, where the acid and its conjugate base are different colors. Okay, so that's why, that's why you have two different colors. In the case of phenolphthalein, one form of phenolphthalein is colorless and the other is pink. But there's many other indicators besides that one, okay? An indicator changes color where the pH of the solution is equal to pKa for the acid. And when I say pKa for the acid, here we're talking about the indicator, because indicators, guys, are themselves weak acids that we add in low concentration. Okay, pH is equal to pKa for the acid, or in other words, guys, what is this point? Where the pH is equal to pKa, that's the halfway point, okay? At the halfway point, the concentration of the acid, and when I say acid here, guys, we're talking about the indicator, of course, is equal to the concentration of the basic form of the indicator, okay? So where those two quantities are equal, where the acid that is an indicator there is halfway titrated, okay? So let's take a look. For this titration, where the end point, or rather not the end point, rather, but the equivalence point happens when the pH is equal to 5.27. We want to find an indicator that is going to change color over, somewhere in that range. Okay, so let's look at this picture. This is a table out of your book. This is back in somewhere in chapter 17. If you look through, I'm sure you just kind of flip through the pages, you can find it. You want to see, what this chart shows you here is the different, color changes and different colors that an indicator can be at different pHs. So, for example, if we look at crystal violet, which is a really cool indicator, at a pH of around, if you look over here, at about 1.6 or something like that, it's like a blue color. Over here, at a pH of like 0.5 or something, it's yellow. And at about 1, it's like green. So it has multiple color changes, okay? If you look at phenolphthalein, the one that we use most often, at a pH of like 8.5 and below, it's like colorless. And at a pH of like 9.5 or something, it gets really pink. So this is a good indicator if the pH at equivalence is like 9.5 or something like that. Or, somewhere like, 9 to 9.5. You can see here it gets kind of pinkish. Okay. But, that's not a good indicator for this titration. If we look, the best two, if we just kind of look here at our thing, are probably going to be either methyl red, because you can see it changes color in this range. That's where it starts to change colors, like 5.2, 5.3 or something like that. Ariochrome black wouldn't be too good, because if you look here where it starts to change colors, like a pH of about 5.5. But also if we look here, guys, bromocresol green. Here it's a green color at a pH of like 4.7 or something, and then it changes very rapidly to blue at a pH of about 5.2. So either bromocresol green or methyl red, these are going to be your two best choices of an indicator for this titration. Hopefully, guys, that makes sense. And there's a whole spectrum of indicators for use where, for different titrations where your pH is going to be at a different range at the equivalence point. Okay. That's part C, or part D rather. Part E, the last part, the most difficult part. This is a great problem. It says to calculate the pH of the solution after adding a 5, 15, 20, 22, and 30 milliliters of the acid, and then we're going to make a titration curve afterwards. That's what the other thing it says. It says make titration curve from the data. Okay, we're going to do that last. Let's do this part of the problem. We're only going to focus on a couple parts because you're going to see that it's a pretty similar procedure for finding the pH at each of these different points except for one. Okay, so let's think about, guys, the reaction that is taking place. Okay, we're taking ammonia. We're adding to it HCl. and we are going to make ammonium ion and chloride. Okay. Now, this over here, ammonia, this is a base. And ammonium ion is a weak acid. It's the weak acid that is the conjugate acid of this base right here. So you can think, guys, that at this point here, 5 milliliters of the base added, or 5 milliliters rather, not of the base, but of the acid added, 15 milliliters of HCl added, 20 milliliters of HCl added, 22 milliliters of HCl added. At each of these points, as we continue to add our titrant, the acid, we're going to neutralize more and more and more and more and more of the ammonia. As we do that, we're going to produce the conjugate acid. At each of these points, guys, what we're going to have is a buffer solution. So at each of these 4 points, how you want to find the pH of the solution, the easiest way to do so is to use the Henderson-Hasselbalch equation. The pH is equal to pKa of the acid, which in this case is going to be ammonium ion, plus log of the ratio of the base over the acid. So what we need to know at each of these points to find the pH is going to be the ratio of the base to the acid. I can know the molarities thereof, or I could do this using moles or millimoles, whichever you prefer. I like working here with millimoles because it is easier for me to do, and so I am going to do that. But you guys at home can do it however you see fit. Okay, so here we go. Let me show you how I'm going to do this. Okay, I'm just going to write down here, and I'm going to make a column here for pH. We're just going to do this here as a table. This is somewhat of a stoichiometry problem, guys. Okay, now here we go. Initially, before we do anything, guys, I want to know how many millimoles. I'm going to make a table here. I'm going to show the number of millimoles of my base ammonia that I've got. Okay, well, I started with 25 milliliters. Okay, the concentration was 0.11 molar, right? If I multiply those two together, what I'm going to get is I'm going to get 2.75 millimoles of my base that I have initially. Okay, now this is the same thing as saying 0.00275 moles, or maybe I'll just write that over here. It's the same thing as saying 0.00275 moles of that base, but since I think millimoles are easier to understand, I'm going to work with that. So initially we have 2.75 millimoles of this. We have none of my acid has been added yet, and I don't have any of this at the end, and so the pH, like we said here at the beginning, was 11.15. Okay? Now let's look at what happens. After I add 5 milliliters of the acid, okay? So here my addition is going to be 5 milliliters. Well, when I add 5 milliliters of that acid, what am I really doing? Well, I'm really adding some number of moles of the acid. So 5 milliliters times the concentration, which is 0.10 molar. That's the molarity here of my acid. This is 0.5 millimoles, okay? When I add this number of millimoles of my acid, it's totally going to react, to the extent that it can, with the base. When it does that, this gets consumed, okay? So if I add half a millimole of my acid, half a millimole of this is going to get used up, and I'm going to have 2.25 millimoles remaining in solution. As I consume half a millimole of this, I make half a millimole of this. So I get 0.5 millimoles of this. Now, if I want to find the pH of the solution, this is just going to be the pKa value for the acid plus the log of the ratio of the base over the acid. pKa for that acid, let's just calculate that really quick. Okay, that would be negative log of 5.6 times 10 to the minus 10th power. That is 9.25. Okay, 9.25 plus the log of the ratio of the base, which is 2.25, divided by the acid, which is 0.5. And we get that the pH is 9.91 or so. And there we go. That's the pH of the solution, guys. Now you can see that at each of these other points, it's going to be a very similar process because we have a buffer at each of those points. So let's just do one more together. Let's look at the pH after I've added 15 milliliters total of the titrant. Well, guys, an addition of 15 milliliters of the titrant corresponds to an addition of 1.5 millimoles of the titrant. If I do that, 1.5 millimoles of my original ammonia gets consumed. So I will have 1.25 millimoles left, and I'll have 1.5 millimoles of this after the reaction. I can find the pH again using the Henderson-Hausbach equation. Okay, again, like that. And if you do that, the pH you're going to find is 9.17. And there we go. That's how you do this part of the problem. Now, the last one I want to look at, and you can see the 20 milliliters and 22 milliliters is going to be the same procedure. I want to look now, guys, at this point right here, after the addition of 30 milliliters of my acid. Now, why do I want to do that? Because 30 milliliters of the acid corresponds to an addition of 3 millimoles of the acid. Okay? Now, you can see that after adding 3 millimoles of the acid, this is all going to get used up, right? Okay, so let's go on to a new slide. I need some more space here to write. Okay? After I've added 30 milliliters of the acid, we said this is 3 millimoles of the HCl. Let's look at what happens. I'm going to write down my reaction again here really quick, guys. So ammonia plus HCl goes reversibly here to ammonium ions plus chloride. Okay, and I'm going to make myself an ice table. I'm going to make it with my little lowercase letters here to denote this is a stoichiometry ice table where I've got moles or millimoles. I said here that we started with 2.75 millimoles of my ammonia before any reaction happened. That was what was present in the original solution. I'm going to add to this 3 millimoles of my HCl. Now, when I do this is going to totally react with the ammonia, okay? And so this all gets used up. So the change is negative 2.75 millimoles. And the change here is also going to be negative 2.75 millimoles because for every 1 mole of this, guys, that gets used up, 1 mole of this gets used up. Okay, so at the end, I have none of this, and I have 0.25 millimoles of that left. And also, you can see that I'm going to make 2.75 millimoles of this, and so at the end, I'm going to have 2.75 millimoles of ammonium as well. Okay, now here's how to find the pH of the solution. I have, at the end of the reaction, you can see I have HCl left over. This is an acid, of course. I also have ammonium ion left over. This is also an acid. I have 2 acids in solution. Now let's think about it though. Which of them is going to control the pH of the solution? Ammonium is a weak acid. HCl is a strong acid. Because HCl is a strong acid, this is going to control the pH. And while I do have this floating around in solution, this is not going to affect the pH appreciably. And so we can sort of ignore this and focus on my HCl. Okay? So if I want to know, the pH of the solution, guys, pH is equal to negative log of the hydronium ion concentration. Okay? Well, this, guys, my HCl that I have left over, that's going to be the main driver of the pH. This is going to be what produces my hydronium. Okay? We need to know here the concentration. I have this many millimoles. Okay? 0.25 millimoles is the same thing as saying 0.00025 moles of hydronium. I'm going to divide that now by my total volume of the solution. After adding 30 milliliters of the titrant, we started with 25, so the total volume here is going to be 55 milliliters, which equates to 0.055 liters. I can go through here and calculate the concentration of hydronium now. This is going to be 0.00455 molar. Okay. Now, an easier way I should do this, guys, is if I took the millimoles, which is going to be 0.25 millimoles, and I divide this by milliliters. The total volume in milliliters is 55 milliliters. That also gives me molarity. And this is going to be the same numerical answer, 0.00455 molar. Just some shortcuts for you guys there. Okay? Now, if I calculate from that the pH, guys, we're going to see that the pH of the solution is 2.34. And there we go. That's correct. Now, you're going to notice here, guys, this is an acidic pH. And that makes sense, though, because this is way past the equivalence point. Here in the titration curve, we have gone past the equivalence point. We've used up all of our base. And now the solution we would expect